So we have one topic left, and that's conservation of energy. So our conservation of energy equation tells us that the non-conservative work done on an object, that's all of the work done by non-conservative forces, is equal to our change in kinetic energy plus our change in potential energy, and that is equal to the change in the energy in the object. So if there's non-conservative work, if it's positive, it increases the energy in the object, and if it's negative, it decreases it. Now, the total energy in the whole system is still conserved, even if it's lost to the object. So for instance, if you're pushing something along and there's friction, then the friction does negative work. If that was the only force, it does negative work. It decreases the energy in your object, but the total amount of energy is still the same. It's just some of it is lost to heat or to other unusable forms of energy. Okay, now we have two types of potential energy. We have gravitational potential energy, which is given by our mass times our acceleration due to gravity times our height. And this can be scaled by a constant, since our actual observables, things that we can measure, only depend on the change in potential energy. You can scale it by an overall factor and it doesn't matter. The other type is our elastic potential energy. So this is the potential energy involved in either compressing or stretching a spring. And it's given by 1/2 the spring constant times the distance away from equilibrium squared. And just like the gravitational, and you can add an overall constant to it and it doesn't change anything. Okay, now let's do an example. Let's say we have a mass that starts at the top of this incline. This incline is 15 degrees. This other incline is 15 degrees as well. And it starts at 4 meters over the ground. And this distance is 8 meters. And we want to know, how high does it rise on the other side of this? Okay. How high does it rise when it gets to the other side of this ramp? And let's assume that this is frictionless. So the first thing we have to do if we're working one of these problems is ask, is there any non-conservative work? If there is, then there'll be a number here. If there's not, it means that our change in energy in the object is 0. And so we can just use the fact that if you add these two changes together, you have to get 0. Okay, so what are the forces that are on this object? Well, there's gravity, which is going straight down, and there's the normal force, which at least at this point, points in this direction. It's always perpendicular to the surface. So as it slides down here, it'll change to be straight, and then as it slides up here, it'll change to be our other direction. Now, these are only two forces. Now, gravity is a conservative force. That's why it has a potential, and that means it is not included in our non-conservative work. Now, the normal force is a non-conservative force, but as we discussed before, the normal force never does any work. So in this case, our non-conservative work is 0, which means our change in kinetic energy plus our change in potential energy is 0. Or written another way, our initial kinetic energy plus our initial potential energy has to be equal to our final potential energy or final kinetic energy plus our final potential energy. Okay. Now the next thing we need to do on any work problem that involves gravity is decide where to set y equals 0. Because you can add a constant to our potential energy here, it does not matter where you set it. But the easiest thing to do is to set the lowest part in the problem to y equals 0. So in this case, our little horizontal piece here, we can set that equal to y equals 0. And we'll use our normal coordinate system where y is vertical, up is positive, x is horizontal, and to the right is positive. Okay, now this thing is released from rest at this point, which means that our initial kinetic energy is 0. And our initial potential energy is just our mg times our y initial. In this case, that'll be 4 meters. Now that has to be equal to our final kinetic energy plus our final potential energy. But we want to know, how high does this thing slide? When it gets to its highest point, when it's sliding here, it'll stop at that point. So the velocity at the point we're looking for is 0, which means our final kinetic energy is also 0. So this has to be equal to our final potential energy. Now, this is a very simple equation to solve. The n's and the g's cancel. And so our initial height has to be equal to our final height. This is because the change in energy in our object is 0. It hasn't changed at all since there's no non-conservative work, which means whatever height it is at initially, that's the same height it'll get to finally. This would also be true even if this angle was different. The height would be the same. The distance on the ramp would change, but the height would be the same. Okay, so this is a pretty trivial problem. So let's spice it up. And we can spice it up by adding friction. So let's say we have a coefficient of kinetic friction of 0.2. Okay, everything else will stay the same. We'll keep y equals 0 be the bottom of this ramp. But now we have to break this problem up into 3 different parts. So because we have friction, if we redraw our free body diagram, we have the normal force, we have weight, and we have our kinetic friction now. So this is our free body diagram on this part of the ramp. Now, when it gets to the bottom, it'll change. Now the normal force is directly up, weight is directly down, and our kinetic friction is pointing horizontal. And then when it gets to the other side of the ramp, it'll change again. So on here, our normal force will be up, our friction force will be back, and weight will still be straight down. So we have to break this problem up into these 3 different sections. There's the section on the first ramp, there's the section on the horizontal plane, and there's the section on the second ramp. Okay. So let's do our first part first. So our first section will be from this part along this ramp until the bottom here. Okay. So we're not any of this horizontal part, just from the top of the ramp to the bottom. So in that case, this free body diagram is true for the entire trajectory of this part. Okay. All right. Now, same question before. Is there non-conservative work? And the answer is yes. There's the same forces as before, but now there's also friction. So we saw before that the work done by friction is minus the force of friction times the distance traveled. So let's find the force of friction first. We know that the force of kinetic friction is our coefficient of kinetic friction times our normal force. So if we write a coordinate system like this, where our y prime is horizontal to or is perpendicular to our surface, and our x prime points down the surface like this, then we can sum our forces in y prime, and we'll see that we have the normal force pointing along positive y, and we'll have this component of gravity, mg cosine of 15 degrees, which will point down. So we'll have a negative, down as in the negative y prime direction. And this thing is not accelerating off of the surface as per usual. So our acceleration in this direction is 0. So our normal force is mg times cosine of 15. Now we also need to figure out what the distance is. So our height is 4 meters, but the distance is the actual physical distance traveled down this ramp. So if we draw that, we have this triangle, this right triangle. This distance is 4 meters, and we'll call that y initial, because that's also our initial height. Our angle here is 15 degrees. And so what we want is the actual distance that the box traveled. The box travels down this ramp. So we know that sine of 15 degrees is our initial, our opposite side, divided by our distance. So that means that our distance then is our initial y divided by sine of 15 degrees. Okay, so if we put that all together, then our work done by friction is minus our coefficient of friction times our normal force, which we found was mg cosine of 15 degrees, multiplied by the distance, which is our initial height, divided by sine of 15 degrees, or written a different way, this is our coefficient times mg times our initial height divided by tangent of 15, because sine over cosine is tangent. Okay, now this thing has to be equal to our change in kinetic energy plus our change in potential energy. Now we called the bottom of our ramp y equals 0. So our final potential energy is 0. And we started from rest, which means our initial kinetic energy is 0. So we have our non-conservative work that has to be equal to our final kinetic energy because our initial is 0. And then our final potential energy is 0. So we only have the initial left. So it looks like this. Okay, now notice that the m's cancel. So we don't know the mass of our object, but we also don't need it. And everything else is just a number that we're given. The only thing we don't know is our final velocity. So our final velocity is plus or minus. Remember, energy always gives us a plus or minus. It can't tell us the direction of 4.46 meters per second. Now, because of the way we set up our coordinate system, we said that this direction was positive. Once this thing slides off the end here, it'll be going in that direction. So our velocity is positive 4.46 meters per second. Okay, so now we're on the second part of the trajectory, this part that has this horizontal part, and then at the end we have this ramp. And so what do we know? We know initially, as soon as it gets onto this horizontal part, it's moving at our 4.46 meters per second. And our second part here will just be our horizontal part. So we don't care about this part yet. We only care about this part. So let's redraw our free body diagram. We have our normal force, we have our weight, and we have our force of friction. If we sum the forces in the y direction, we see that the normal force minus our weight is equal to 0, or the normal force is equal to mg. Okay, so our work done by friction is minus our coefficient of friction times mg times the distance that we've traveled. So that'll be the distance of this entire horizontal part, which we said was 8 meters. And this is equal to the change in our kinetic energy plus our change in potential energy. Now we said this horizontal part was y equals 0. Since we're always staying on this part, our change in potential energy is 0. It's 0 when it starts, and it's 0 at the end here when we're at the end of the horizontal part. Okay. So this is just equal to our change in kinetic energy, which is our 1/2 mv final squared minus our 1/2 mv initial squared. Okay. Now we know what our initial is. It's our 4.46 that we found before. It was the final of the ramp part, but now the initial part of this problem. Once again, our m's cancel. And so all we're left with is v squared. That's the only thing that we don't know. So if you plug in all your numbers, then you'll find that our final velocity squared is equal to negative 11.5 meters squared per second squared. Now I've run into trouble, right? I have a square is equal to a negative number. Okay, that's only possible if we have imaginary numbers. Velocity can never be an imaginary number. So what does that tell us? Does that mean I messed up a computation somewhere? Well, if you were doing this on the test and you wound up with this, that is certainly a possibility. but I've done it more than once. I'm confident that this is a negative number. So what's the alternative solution? The other thing that it could mean is that your block doesn't make it all the way across. So friction takes away so much energy from our block that it actually doesn't make it all the way to the end of our horizontal bit. So let's do something a little different then. Since we can't tell how high, then let's instead say, how far does it go? So it doesn't make it all the way here, which means at some point it must stop. So our work done by friction has to be our change in kinetic energy plus our change in potential energy. We're still on the horizontal part, so this part is 0. You don't have to worry about that. And since we want to know where it stops, then our final velocity is 0. So we saw before that our work done by friction is our minus our coefficient times our weight, since we're on this flat part, times the distance that is traveled. Now this time, this distance is not our 8 meters, but rather it is a variable and we don't know how far it is. That's what we're looking for. So this has to be equal to our final kinetic energy, which is 0 since our velocity is 0, minus our initial, where our initial was that 4.46 that we found before. So once again, our masses cancel. The only thing we don't know is our distance. So we can solve for that. It looks like this. And so if you plug in your numbers, then you'll see that this is 5.07 meters. So that's how far it got. It didn't reach, it didn't make it across the whole 8. It made it a little over halfway, and then it ran out of energy and stopped. Okay, so that's pretty much how all of these problems work. The only other thing I could ask you is, okay, well, what is the change in energy? And the change in energy is always going to be equal to the non-conservative work. So once again, if it's positive, that means the energy of the object has increased. If it's negative, it's decreased. Okay.